As all the other speakers have, I'd love to thank you for the opportunity to speak here with all these wonderful attendees in this beautiful location. It's an absolutely unspeakably wonderful opportunity. We've heard a lot of talks today about basic science and engineering and quantum systems, about how we can build really fantastically controlled little quantum devices, how we can do computations with them, how we can do simulations with them. We've heard a lot of talks about the physics that goes inside of these devices. I'd like to talk about something a little bit different, actually. I'd like to talk about what happens when we take our focus away from that device. Hopefully, am I holding this upside down? Yes, I am. And even take our focus outside of the physics lab, and we ask ourselves a little bit different question. If we take our quantum computer and we literally put this inside of a box, and we forget about all the things that went inside of it, and we just try to ask the question, what is the basic science that we can do with this quantum computer today as a computational device? So no longer looking at this as a tool for studying the quantum computer itself, but using it as a tool for answering other problems, possibly problems outside of physics, outside of condensed matter physics, using these devices. You can see here, I've literally put our quantum computer in a box. I actually love this photo. It's may not be as beautiful as the Sistine Chapel, but it's quite attractive. This quantum computer is actually at the cafeteria in the Cleveland Clinic. As an experimentalist, I might not have elected to put a dilution refrigerator inside of my cafeteria, but the fact that it's there has an important role. That if we're going to get people doing basic science with quantum computers that aren't physicists, that aren't in this room, then we need to get them interested in these devices. And this is one of the many ways that we can try to build interest in using these new computational methods outside of physics. So what properties do we need to have? What does our quantum computer need to be able to do for us to be able to do basic science with it? Well, these are some minimal requirements. I'm not saying if you meet all of these that you'll get there, but at least it's a good starting point. First of all, you need more than about 100 qubits. That's pretty simple to understand. If you have less than that, then this computer is doing something that can be simulated efficiently by a classical computer. You didn't need the quantum computer to start with. You're just not playing in the right ball field. The second requirement, and this is one where when you talk outside of people working on quantum computing, this seems very obvious, you need it to give you the right answer. To be a little more specific, we need to be able to get accurate expectation values out of this quantum computer. Not perfect. No simulation of a physical system is ever going to be perfect. In the case of an ideal quantum computer, we would still have, for example, shot noise and estimating expectation values. In the case of a classical computer, we have errors because of finite step size and integrators. We have round-off errors. And in any given field, there's a precision which you need before an answer becomes interesting. And so this is a very specific to the type of problem that you're trying to solve requirement, but it is a requirement. And then finally, we need the thing that we talked about at the beginning. We need an interesting problem to map to a circuit, which is ultimately the input that you're going to put into your quantum computer. So you need a problem to solve that you know how to express in a way that is approachable to a device like this. So let's kind of take each one of these requirements in turn. More than 100 qubits. There is a lot of engineering in this problem. There's a lot of basic science in this problem. We've heard a lot about this. It's things not just inside of the quantum processor that we heard a lot about from John earlier, but also things like quantum unlimited amplifiers, like we heard about from Irfan, software, space transformers, control electronics, an enormous amount of engineering. I like to say that all of this engineering features a little bit of an Anna Karenina problem, that you need to get all of these things more or less right at the same time before you have a functioning system. This is a pretty tricky problem, but it's really not the topic of this talk. I should mention I come from the hardware side of IBM, so if you're interested in any of these things, I would love to talk to you about this over lunch, just not what we're doing today. The second thing that you need is an accurate answer. And we've had a lot of talks already this week on this topic. With currently available devices, the error rates are pretty high. If we take the processor that I'll be talking about mostly, which is IBM's Eagle processor, has about a 1% 2-qubit error rate. And so if I imagine doing a circuit on a 127 qubit device that's just 10 layers of gates deep, the fidelity of the answer that we get at the end is going to be about 7 times 10 to the minus 4, or in common language, wrong. And so we absolutely need to do something to deal with the noise that's coming from the errors in our computation before we can get an accurate result out. And we've heard a lot about these techniques already. We've heard about error suppression, We had some absolutely beautiful results on air detection, error correction for Misha. I'm going to be focusing on a different set of techniques called error mitigation. And these are techniques that ask the question, are there things that we can do with our processor where we're going to trade additional executions of the circuit against getting a higher quality answer out of it? We're not going to try to correct all errors perfectly. We're just going to try to get a better answer out of this. To understand a little bit better, I'd like to start from kind of a simplified, very, very simple toy problem. Let's imagine I have just one qubit, and this qubit has only bit flip noise. And I'm going to try to correct that bit flip noise. So with a probability of p, my qubit gets an X gate on it, gets flipped. With a probability 1 minus p, nothing happens. And the strategy that I'm going to use is to probabilistically, so at random, classically random, insert a gate into this circuit to try to invert that noise map. Some of you are hopefully a little bit mad at me because you know that noise maps aren't invertible, but let's just go ahead and try it and see what happens. So as an ansatz, the gate that I'm going to insert will be another X gate. So on each shot of the circuit, I'm either going to deliberately flip the qubit myself, so the same as the noise channel might have done or not. So with a probability of 1 minus q times 1 minus p, I don't flip the qubit, the noise doesn't flip the qubit, nothing happens, we get a good result, we're happy. With a probability of q times p, the noise flips the qubit and so do I, and again, we get the correct result and nothing happens. But there's two different outcomes where we have an error. One is where I flipped the qubit, but the noise didn't. And the other was where the noise flipped the qubit, but I didn't. And you can see those have different probabilities, 1 minus q times p and q times 1 minus p. So if you do a little bit of algebra, you can work out how often I need to flip the qubit in order to cancel the effect of this noise. And you get the answer that the probability is for small values of p, so for small error rates, roughly minus the probability that the noise flipped the qubit. Now, we asked some interns to go out into the lab and try this. And we told them, flip the qubit minus 2% of the time, and they got a little bit mad at us. They didn't know how to do that. And that actually brings us to kind of the big first limitation of this type of error mitigation. And that is that you can't do this on a single shot of a circuit, that you can't do this if you're interested in a sampling problem. However, if what you're interested in is an expectation value, the average value of some observable at the end of your circuit, you absolutely can do this. And the way that you do this is by taking a weighted average. That you take all of the cases where you did not flip the qubit, and you include those in your weighted average with a positive sign. You take the cases where you did flip the qubit, and you include them in the weighted average with a negative sign. And the net result is that you get the same expectation value that you would have had you been able to do that flip with a negative probability. Now, because I'm now taking a weighted average of a set of outcomes, some of which have positive signs and some of which have negative signs, when I do that, there's going to be a denominator that's less than 1. So in effect, I'm taking a whole bunch of outcomes from my experiment, I'm adding them, subtracting them from each other, and then I'm dividing them by a potentially very small number. And so dividing by that number increases the variance in my outcome, increases the variance in the expectation value that I have, and it's the main cost of taking this approach. That I have to take more samples of my circuit than I would have had to otherwise had I not been doing this to overcome that additional variance. The second main cost of this approach was implicit in my setup of the problem. Before I was able to pick that probability Q, I had to know P. In order to do this type of error mitigation, you have to very precisely know the error model of your device. You have to know each type of error that it is subject to. You have to know the probability with which it commits those errors. And then the final thing, which goes without saying in that error model statement, is the error model can't drift. It has to be a Markovian. It has to be the same over the course of your experiment. But if you can make sure that all those things are true, you can actually demonstrate that this approach will give you an unbiased estimate of an observable. So error mitigation done this way will give you the correct answer. Furthermore, you get the error bars because you can propagate errors from your error model through to your final result. It's actually a very nice technique. In practice, it works pretty well. Here's a very simple toy demonstration. What we've done here is taken a 50-qubit circuit, and we've just used 2 control knots to make a very complicated identity operation. Going from left to right here, we're just looking at different weights of observables like Z, ZZ, ZZ, ZZ. We'll all fall asleep as I say more and more Z's. These should all nominally be 1 because we've constructed an identity operation and started from a Z eigenstate. You can see without PEC, because our processor, as I said before, very noisy. As we go to these very high weight observables, we essentially never get the correct answer. With PEC, we see the expectation values remain close to 1. This was a very early demo. You'll notice there are no error bars on that. That'll be corrected later. Now, for the sake of understanding what I'd like to talk about next, another approach that's sometimes used is something called zero noise extrapolation. It's another error mitigation technique, and it's based off of a very simple observation that if you have a circuit with some noise model, your observable at the end of the day is a linear function of the noise. And so in principle, if somebody hands me a knob that I can use to turn the noise up and down, I can turn it up and down and look at my observable. And if that knob has good calibration, I can then extrapolate back to what that observable would have been in the presence of zero noise. This is typically a very difficult experiment to do because you need to identify that knob and you need to calibrate that knob. People frequently use the length of time used to run the circuit. As you run it more and more slowly, decoherence adds up and your error rates go up. You run it faster, the error rates go down. There's a limit to how far you can go there. We can't run the gates infinitely fast because the error rates go back up again. Otherwise, we would run them infinitely fast. And so you have to use a very enlightened guess over what range of run times to use for this to work. It's sort of a dangerous technique. However, if we take these two techniques and we put them together, the probabilistic error cancellation that we talked about before and zero noise extrapolation, we end up with an interesting intermediate technique. Here, what we're going to do is characterize the noise model of our device very well, exactly as we would have had to were we going to do probabilistic error cancellation. And we could have an entire seminar on how to characterize that noise model. And then instead of using randomly inserted gates to turn down the noise, we'll randomly insert operations to turn up the noise. That gives us an exquisitely well-calibrated noise knob. I know exactly where 0 is. I know exactly where it is with my nominal operation. And I can turn up the noise in teeny tiny increments by adding these gates at random. And so this is an extremely well-controlled version of this zero noise extrapolation. We call this probabilistic error amplification, and it's what's going to be used for all of the rest of my talk. So the final problem that you need is an interesting problem. Unfortunately, for our internal demonstrations, our problems are generated by physicists, and so we end up with interesting problems like the 2D icing model with a transverse magnetic field. So possibly this is not the most universally interesting model, but it's at least one that our experimenters understand. And what we're going to be looking at specifically is the time evolution of a spin state in this 2D icing model from an initial starting state that's not the ground state. So this is a computationally non-trivial problem. In order to do this on our quantum computer, what we're going to do is layers of gates that actually initialize the qubits in that starting spin state. We'll do layers of gates that actually simulate the Hamiltonian evolution. Now, we do not have a gate on our quantum computer that is dz plus x. It's not one of the ones we calibrate up. And so we use a technique called trotterization to get this dynamics, where what we do is we apply a zz operation for a very short period of time, an x operation for a very short period of time, and alternate back and forth between those. Those operations don't quite commute, but the error, because of not including that commutator, is quadratic in how small these steps were. You can get a pretty accurate answer. Just to give you a picture of the 2D lattice we're using one that corresponds exactly to the lattice of the qubits on our devices. That's one of the many small ways in which we've loaded the dice in our favor in this demonstration to give ourselves a system that we can simulate very efficiently on our hardware. But that's the topology that we're using. So at the left, we're looking at the magnetization, actually the total magnetization in this case, the magnetization of a specific qubit at the end of 15 trotter steps on a 127 qubit device. The x-axis here is the transverse magnetic field applied, and the y-axis is that magnetization. So the kind of interesting thing here is for a zero magnetic field and a magnetic field of pi/2, where here I'm measuring it at how much rotation it gives us per trotter step, this circuit turns into a Clifford circuit, and it's trivially efficiently computable. And so we can confirm that we're getting the correct answer from our error-mitigated quantum computer. For intermediate values of this transverse magnetic field, it turns out, although this system is too large for us to efficiently simulate on a classical computer, we can take advantage of a light cone simulator. And in fact, our collaborators at the UC Berkeley, who are shown on the slide here, helped us enormously with this, and also with using various classical approximate methods to simulate the system. And you can see with this light cone simulation, light cone optimization, we can confirm that we are getting accurate estimations, accurate expectation values for this magnetization at the end of these 15 Trotter steps. At the same time, some reasonably chosen approximate methods, including John's favorite matrix product states, as well as some tensor network methods with finite bond dimension, are failing to accurately capture the dynamics of the system, even at this relatively small depth. Now we can go a little bit further. I don't have any beautiful animations of atoms moving around like Misha did, but I can show you a picture of a very large circuit. This is that 127 by 15 entangling layer circuit. This gives you a feeling for how many non-Clifford operators and 2-qubit gates there are in the circuit. But we can go all the way up to 127 by 62 depth. This is deep enough that these light cone simulations are no longer enough to exclude any portion of the device. And when we do so on the right, you can see that we've lost our exact simulation except for those special points 0 and pi over 2. And we can see once again, we're getting mitigated values out of our quantum computer. We have error bars on those from our probabilistic error amplification. So we believe these results are statistically significant, and they differ from the approximate classical methods, which is not surprising. Those methods had already failed at a depth of 15. We can also go beyond exactly verifiable by, instead of looking at the magnetization of a single spin at the output, we can look at correlations between many spins. Again, just a way of defeating these light cone optimizations, and once again see that our results vary wildly from the classical approximate methods. Now, if there is only one thing that you believe or take home out of this talk, if that thing is that we can use a near-term quantum computer and, despite the fact that it has errors, extract an accurate expectation value, I think that's huge. That says that when we talk about near-term quantum computing, and at IBM we're not allowed to use this phrase, we call it noisy intermediate scale quantum computing, we're really missing the point. It does not have to be noisy. You just have to be adequately clever in how you use the computer to remove that noise, and you can still get an accurate answer out of it. So one thing to take out of this talk. Now, we published this paper a few months ago, and there was actually a flurry of follow-on publications. I believe this was about 2 weeks after the publication this plot was prepared. All of those additional curves are new approximate methods for simulating this kick dicing model, which is something I never thought anyone would be interested in doing. And the interesting thing is, out of these, I think at this point it was 7 publications, every one of them differ from each other by about 20%, but are consistent with the error bars that we were getting out of our exact simulation of this circuit. So, is this a useful problem? Have we done useful basic science with this? Well, yes and no. I mean, we've exactly simulated a quantum circuit that is beyond a classical computer. If you were adequately clever in advance, you could have developed one of these approximate methods and gotten the same answer without the quantum computer. So we're not quite there as far as doing something that could not be done without a classical computer, but we're certainly doing something that was very difficult before this experiment was done. Now, what about the next step? What if we want to go to something where nobody is ever going to be able to show this with an approximate classical method? I'm pretty optimistic. One of the reasons why I'm pretty optimistic is on this slide. Just focus on the plot on the right for the moment, because we don't have a lot of time left. The red curve are the 2-qubit error rates, the distribution across the device for our Eagle processor that I just showed you. And let's not worry about the 2 red curves at the moment. And so you can see there's some distribution of error rates going from about 0.5% to about 2% across the device. The blue curve is a new device that we have in our lab. And you can see actually the median error rate on this device is better than the best error rate on our previous generation of processors. The progress in this field, as we've seen already this week, is enormous on all fronts, and including on error rates. This means we could have run a circuit that was 3 times deeper, which is kind of interesting. We also could have run a simulation of something that didn't quite so directly map to our processor, something possibly more interesting to the scientific community. If we look out a little bit further, we can look at coherence times of qubits. This is one of the fundamental limitations to how accurately we can build our computers. The coherence times in that Eagle device were about 250 microseconds. If we focus on isolated qubits in our lab, we have processes that repeatedly give us coherence times in excess of 1 millisecond, so over 5 times larger. So there's a lot of potential still for improving the fundamental accuracy of these processors. Now, we could also, in addition to that kind of bottom up, are we optimistic from the hardware side of the game? We can look at this top down, and I'm going to show a plot similar to what Carl showed actually yesterday, of if you ask the question, how many qubits do I need and how many gates do I need to solve a useful problem, from the actual people that want to solve those problems as opposed to the people trying to build the computers, you end up with a graph that looks a little bit like this. This is different from Carl's graphs in a couple of key ways. The first is the y-axis here is now qubits, because at the end of the day, qubits are qubits are qubits. They're, degrees of freedom in a quantum computer. It shouldn't really matter to you whether I built a logical qubit like Misha did, or I used error mitigation like I'm talking about today, or I'm using the surface code like Carl and Microsoft are talking about. What matters to the user is how wide of a quantum register they need. And by removing the assumption of a particular error correcting code like Carl had for the surface code, then we make this a much more future-proof graph. I think that hopefully Misha's results yesterday convinced many of the people in this audience the surface code is probably not the direction to go in. The other thing that it does for us is it disentangles the width of the device, the number of qubits, from the depth of the circuit that you need to run. When you reference this to a specific code, as you go to more and more gates in your circuit, you end up saying that you need to have more and more physical qubits because you need more error correction once you start talking about a specific code. And so you end up with kind of strange answers like there are no interesting basic science applications before you run into cryptological applications. And the reason why that's happening is if you make some set of assumptions about how many physical qubits you need to get to very deep circuits, then you end up getting a quantum register wide enough to solve those applications. But you can see here, actually, for computers of sort of 100 to 1,000 qubits of any type, however you're getting these accurate answers out of them, there are a lot of interesting problems in spin systems and material science and in chemistry that you can hit on that smaller quantum computer without ever having come near any cryptological applications. And remember, the axes on this plot are not equivalent. If I want to build a computer with 10 times more qubits, to go to John's economic arguments, I need 10 times more money. But if I want to run a circuit that's 10 times deeper, and I'm using error correction, that could actually be a fairly small change in the underlying physical error rate of the system. It's much easier, once we get error correction, to move to the left or the right on this plot than it is to move up and down. So I'm very encouraged about this, both from the viewpoint of our underlying systems are getting more accurate. We're continuing to see rapid progress in fidelity and in coherence times. And we're really rapidly approaching these points where practical applications become possible. I should mention the white dot on this plot is approximately that utility paper that I just showed you. And that's about 7 hours of execution on our quantum processors today. So, in the spirit of some of our discussions of history, I just wanted to include this. We've been working on quantum computers for a long time at IBM, and there are people in this room that have been working on circuit quantum electrodynamics for even longer. It's kind of amazing how far we've come, that device on the left from 2010 is a single flux qubit. That was actually the cover of Physics Review Letter, by the way. That kind of beautiful circuit board. And on the right, we have our 433 qubit Osprey processor. That's 12 years of progress. And so when we talk about whether we're going to reach quantum advantage yet, or error-corrected quantum computing yet in the next 12 years, and I imagine that much progress again, I'm very happy, I'm very excited. So thank you all for your attention, and